Okay, so welcome to Physics Live once again. Today we are going to discuss something interesting regarding the quantum mechanics. As it is well known to you that we have already discussed so many things about the quantum mechanics, which was just preliminary steps to understand what is this, what is the application of Schrodinger equation, and the main thing in the quantum mechanics, as we have already discussed, that we have to only solve the eigenvalue equation, which is nothing but h psi equal to E psi, which is the time independent Schrodinger equation, where obviously the h is the Hamiltonian operator, is the total energy, as we have already discussed. So what we have observed, that by changing the potential, uh, that is, this can be explained like this, and the potential energy is always changing in every problem, and due to this change we are getting some different wave function of the system as well as the different energies. Okay, so till now what we have discussed, the 1D potential box and the extension of these in the 2-dimensional and 3-dimensional cases, as well as we have discussed the harmonic oscillator case and the hydrogen atom case. All these are something identical, but it is already known to you that there is no identical case in reality. We all know that every one of us should not lead an ideal life. Some perturbation should come into the picture. So but the introduction of these perturbating terms or some deviation from the ideal nature, we have to modify our process. But then why, you may ask me, that why we are studied this type of ideal situation, that the potential is zero somewhere and out of this region the potential is some infinite. Why we are studying these things? This is so ideal case. As well as you can also assume that we have already discussed that the intention of the study of the harmonic oscillator type of potential. So I am not going into the details about it. You may recall, either you may recall or you can revisit the lecture once again. Okay, then now it is the question that why we are considering this type of ideal situation at all while discussing the 1D potential box. Some potential may be there like this, some potential may be like this, it may happen. Then why we are treating this ideal type of situation and why we have solved this ideal type of case? The simple reason is that our intention in the actual problem is to just modify our unperturbed system or the ideal system. Okay, so the solutions that we had already obtained in case of the ideal cases, that is the psi and the E, we have to just modify this with the help of certain process, out of which one of the approximation I have already discussed with you, that is nothing but the perturbation theory. For those who are new to this channel, you can revisit the perturbation theory, which has already uploaded many times ago, and you can see it, which is readily available in the YouTube in my channel. So you can revisit the lecture once again. Okay, so in this lecture we are going to discuss some other approximation that are available with us. Okay, and then finally we are come to the one interesting theorem, which is also known as the Feynman-Hellman theorem, and some important application of it. Okay, so let us go into the details about today's lecture. So, approximation method. There are various approximation methods available with us. First one is that we have already discussed, perturbation theory, which is very much important and very uh, which gives us very fruitful result. Perturbation theory, it contains both the time dependent which is known as time dependent perturbation theory, and time independent perturbation theory. Out of which we had already discussed the time independent portion, which is somewhat simpler than the time dependent, and we are going to soon discuss the time dependent part in another video. So today we are mainly focused to discuss the variation method, variational method. Okay, so what is this? It is better to mention that, like the perturbation theory, you can get the first order correction, second order correction, and find the any energy level. You will able to find the any energy level correction by using the perturbation theory. For that, what you have to just apply, you are going to get some unperturbed energy level by solving the ideal Schrodinger equation, considering the system to be ideal, and then just add this corrected term using some approach that we had already discussed. So you have to just find the correction in the energy level by the use of the perturbation theory, and just add to the unperturbed energy level, so that you can get any correction to the any energy level, that it may be ground state, it may be first excited state, it may be second excited state, and so on, because it is dependent on the n, and you can easily find out the any corrections of any energy level. But in the variational method, it is exclusively applicable to find the ground state energy of the system. Ground state energy of the system. So you cannot get the first excited or higher excited state energy level by using this method. Okay. So it is the first point to mention, that it will not help us to evaluate energy levels or wave function of the system. It does not give us these things for the practical case that we are going to consider, but we can get only ground state energy. How? By considering some trial wave function. What are all these things? We are going to discuss soon. So let us discuss these things. So what I mean to say, we are going to calculate the ground state energy. How? By using the expectation of the Hamiltonian available with us to the system, because in every system you can easily find the Hamiltonian, at least you can find the Hamiltonian, but the solution of this, it will be hard to calculate, or it is hard to be solved, but you can always get the Hamiltonian of the system. Okay, so if you have the Hamiltonian, and if you consider the trial wave function. How you can guess the trial wave function, I will also going to say this, but now simply you have to consider some trial wave function which will be available with you, and the Hamiltonian which is also available to you with the known with the knowledge of the system which you have considered. So you will get the ground state energy to be something like this. Now this is not the ground state energy, this is the expectation of the Hamiltonian with respect to your trial wave function. Okay, so I would like to write in a proper way. So let us suppose this is the expectation value of your Hamiltonian corresponding to your trial wave function, like this. Okay, now this theorem tells us that your ground state energy of the system that you consider will be less than equal to the this expectation energy, expected value of the energy with the application of your considering Hamiltonian. So in another words, you can say that E naught is nothing but the upper bound of the ground state energy, upper bound of the ground state energy of the system that you are considering. Okay, now what you have to do, the next question is which comes to your mind, that how to guess the trial wave function. Up to this point it is clear that we will consider some trial wave function and then find the ground state energy by simply doing the expectation of the Hamiltonian with respect to the trial wave function. But how to get this? Okay, for that we will going to discuss the proof of it. So proof. Suppose you have a complete set of eigen state for any Hamiltonian, known Hamiltonian H, which is easily solvable in the by the application of the Schrodinger equation. So for that you have the complete set of psi available with you. So all of this will satisfy the orthogonal condition, which may be 1 for m equal to n and 0 for m not equal to n. Now you also known that the projection operator, this is not the momentum operator, I have defined it with the small p as the projection operator. Rather you can remove this confusion by considering the projection operator to be capital P. So it may be simply given as outer product of psi I, psi I. Okay, and it is also known to you by the completeness relation that this is equal to identity matrix. So we are going to all these things, we are going to apply all these things. So you can write any wave function psi by the in the form of the elements of the Hilbert space. This is the linearly independent orthonormal basis of the Hilbert space, and we can expand any wave function available in this Hilbert space in this basis by where Ci is the Ci gives the probability with which of occurring psi I. And how we can calculate the Ci? It is very simple. That psi you can write as psi I 1 to n psi I. Okay. Now this thing is 1. So the left hand side and right hand side are equal. Now what you can do, it is simply the inner product, so you can readily take it out. So you can write that psi is sum of I will not write the limit, so psi I psi psi. So this gives us nothing but some number which is dependent on this psi I. So you can write this as sum of ci psi I. So if I am going to expand this, psi will be c1 psi 1 c2 psi 2 c3 psi 3 and so on, cn psi. Similarly, taking the conjugate of this, c1 star psi 1 c2 star psi 2 cn star psi n. So if we assume that psi is normalized state, then what we can write, that psi inner product of psi should be equal to 1, or in another words, this entire thing okay, let me write in c1 star psi 1 c2 star psi 2 psi n cn star c1 psi 1 cn psi. I have omitted to write the these terms, and it is also known to you that by simplifying this you will able to get equal to 1, which is a kind of obvious, because I have already mentioned that this is the probability of occurring psi. From this thing you can easily get. Okay, so the total probability should 1. Now, but we have to prove that ground state energy is less than the expectation value of this Hamiltonian. Now, the expectation value of the Hamiltonian can be written as what? Psi psi. So again psi is expandable with this relation, so you can write c1 star psi 1 c2 star psi 2 sorry I have this thing and operated on psi c1 psi1 c2 psi2 this. So we can take this inside the bracket and write c1 star psi1 c2 star psi2 this c1 h psi1 c2 h psi2 so on. Now what you will get when h operates on psi1, what it will give e psi1. We don't know the exact value of e, we don't know the exact value of psi1, but it will give this until and unless we are known to the potential, whether it is easy to solve or not, but it will give some energy. This some energy means when it is operated on the first energy eigenstate, then it will give the first energy eigenvalue. Okay, and when it operates on the second energy eigenstate, it will give the this. Okay, and the left portion is remains unchanged. This, so this will simply gives us c1 square, this is scalar, this is scalar, and this is also scalar, so e1 psi1 psi1 c2 e2 c2 square psi2 psi2 and so on. Now all these are orthonormal because we have considered the linear orthonormal basis in the Hilbert space, so these are all equal to 1. So we will get simply c1 square e1 c2 square e2, similarly c3 square e3, and so on and so forth. So we can write in summation format as I ci square ei. Okay, this is the expectation of the Hamiltonian. Now if EGS is the ground state energy, EGS is the ground state energy of the Hamiltonian, corresponding to Hamiltonian H, then what we can write? We will find that EGS is obviously less than equal to the first excited state, obviously less than equal to the second energy eigenstate, and so on. Ultimately we can say EGS is less than equal the ith level energy state. It may be any general. Okay, so what we have we are getting, if we replace the EI by the energy eigenstate EGS and ignoring the effect of less than, just considering the equal to, then we will get H. Okay, if we consider also the less than equal sign also, and what we will get, sum over I ci square, EI is replaced by EGS with greater than equal to. Why the reverse sign is happens here? Because if we multiply these ci squared EGS, this is also less than ci square EI. Now we have this ci squared EI, which is equal to this. So this is obviously ci square ei square is obviously greater than ci square eg square. Now this is equal to what? The expectation of h, this entire thing, as we have calculated above. So more expectation of h is sum over ci square egs. Now what is sum over ci square? That we have already calculated here, that sum over ci square is 1. It gives the total probability. So we can write that expectation of the Hamiltonian is obviously greater than the ground state of the. So our main task is to consider some energy eigenstate which we have defined some trial, okay, and find the expectation of h which will be obviously greater than the ground state energy of the respective system. This is known as the variational principle. If we want to calculate the approximated value of the ground state, then we can use this variational method. Now it will be easier for you if I consider some example of the application of it. So it will be mentioned to your question that consider for a harmonic oscillator using a Gaussian wave function. Sometime it may be asked to you, sometime it may be given to you the ground state energy, the trial wave function, or otherwise you have to assume the trial wave function. So more generally you can consider the trial wave function to be Gaussian, which is nothing but a to the power minus bx square, and we are interested to find the ground state energy of this harmonic oscillator. So where you are known to these things, that is the normalization constant. What is b? B is known to the some parameter which will also known as adjust parameter. Whatever. Okay, adjust parameter. Now the first target is to evaluate the normalization constant. How? Applying the normalization rule. Considering the integral formulation. So psi gs star psi gs dx is rather I can remove this gs because it is a trial wave function. Okay, so this is equal to 1. So mod a square minus infinity minus 2bx square dx is 1. It is a standard integral, so the value of which you are known to this, that pi by a. In the case of a, this is 2b. So what is a? Value of a is 2b by pi 1 by 4. So this is our normalization constant. This is the normalization constant by solving this integral, which is known as the normalization condition. Okay, so let us put this value of a in our trial wave function, then psi becomes 2b by pi 1 by 4 to the power minus bx square. Now still b is unknown to us, so what we will do, we will form the Hamiltonian. So as the system is given to you, the harmonic oscillator, you can easily find out the Hamiltonian. What will be the Hamiltonian? H can be written as p squared by 2m. If the mass if the mass of the harmonic oscillator to be m, then if the mass of the particle undergoing this harmonic oscillator potential be m, then p squared by 2m is the kinetic energy operator, and Vx, which is nothing but half m omega squared x squared. Omega squared x squared, which is the potential energy operator. So this is the Hamiltonian operator of the system, and it will operate on the side. And we are interested to find the expectation of H. So in the integration form we can write this, and H operator we can expand. In the position operator we can write PS minus iota H line del del x. In one dimensional case, ddx you can write. Okay, rather I can say that in 3D this is correct. Okay, so minus H line square by 2m d2 dx2 plus half m omega square x square. This is the Hamiltonian, and by since psi that is psi square, that is 2b by pi 1 by 2 to the power minus 2bx square dx. So I have to solve this integral. So first this thing d2 dx2 of 2b pi, it can be taken outside, so this minus 2bx square. I think some mistake I have taken. So what I will do, these things are very crucial. Okay, so we know that conjugate part will be there, so it will also contain 2b by pi whole to the power 1 by 4. So 2b by pi whole to the power 1 by 4 square means 2b pi whole to the power half. It is okay, but this you cannot take at this. One portion will be there corresponding to imaginary part. Since it is a real function, then no change will occur, and the second portion will be there. So you can write minus infinity a to the power minus bx square minus h line square 2m d2 dx2 a to the power minus bx square, this plus into dx half m omega square. This can be taken outside, 2b by pi 1 by 2. Similarly here it will also be there, 2b by pi whole to the power 1 by 2, and integration minus infinity plus infinity x square e to the power minus 2bx square dx. It is also a standard integration, you can easily solve. I will not do this because some calculation you should have also do. So I will just simply write the solution of this. After simplification, you have to take 2 times derivative with respect to x, then multiplying these things you will be able to, okay, let me write one step further. Minus h line square by 2m, one derivative will bring minus b 2x e to the power minus bx square, and then again you have to take one another derivative, okay, then dx, and it will remain as it is. So 2b by pi whole to the power half. After solving all these things, it will results only let me write the last part only. You will be able to solve h line square b by m plus 1 by 8b. I just want to tell you the power of this method, and the steps you can easily do if you are good in mathematics, and you can easily do these things, but I am just here focusing the method. H line square b by 2m, then it will bring this thing h line square by p by 2m plus m omega square by 8p. Now what according to our theory, we are going to find the ground state energy, so for which the Hamiltonian should be minimum. We are interested in finding the minimum energy, so it should, if we take the derivative with respect to this adjust parameter, then it will result to some 0 because of the extreme condition to find the minimum h. Okay, so if we do the derivative, then what we will observe, h line square by 2m plus minus m omega square by 8b square 0. So what we will get, the value of b square equal to m omega square by 4 h line square. Also, okay, so, and this is also m square, so b will be nothing but m omega by 2h line. So our adjust parameter is coming without with some adjustment, that to satisfy the Hamiltonian to be minimum, it should be for this wave function, then it should satisfy the extremum condition for that adjust with respect to the adjust parameter that we have taken in the trial wave function, and the b also able to obtain. So what are unknown to us in the trial wave function? The two things was unknown to us in the trial wave function. One is a and another one is b. So all these things are known to you now. Now you can easily write, or rather you can now easily find the minimum expectation energy by putting the value of b in the Hamiltonian, what you have obtained here. So h line square by 2m, what is the value of b? M omega by 2h line. What is the value? M omega square by 8 b, m omega by 2h line. 2 to 4 m omega omega 2 sorry 2 h line. So and m, so h line omega plus of, and again this is also 2, so this is 1 by 4 h line omega plus 1 by 4 h line omega, half h line omega. Okay, again it is already known to you from our previous calculation of harmonic oscillator that sorry that En is n plus half h line omega, then the ground state energy is half h line omega, putting n equal to 0. So which exactly match the ground state energy as obtained by the variational principle. Now why this ground state energy exactly matches? Because we have considered the ideal system. So if we add some amount of perturbation to the system and consider the trial wave function, then it would give some different energy which will obviously be less than the expectation. It is the general case, and what we have obtained is the ideal case, ideal one. So it is the power of the variational method. So in our previous lecture we have discussed the perturbation theory, and in this lecture we have discussed the variational method, and now we are going to discuss some interesting theorem which might be helpful in many cases. So till now what we have done, that the solution of the Schrodinger equation, which involves some energy formulation. Now sometime it becomes very difficult to solve this Schrodinger equation, as we have already said, and the energy approach sometimes becomes difficult to us. So in that case we can shift to some different approach, rather we can say that force approach. Now why in general we are not used to take the force approach method? Because of the simple reason that we can think that the force method is sometimes difficult, as it does not relate as the wave mechanics, because the wave equation, the quantum wave equation, which is nothing but the Schrodinger equation, is known to us. So we always tend to approach any physical system by the energy approach method, not the force one. Although the force is more general, because it would gives rise to the explanation of the many phenomena of the molecules, like the stiffness of bonds, valence bonds, bond angle, bond angles, geometry of the molecule. All these things come from the force, contribution of force inside the molecule. But we are not going to discuss, we usually not go into the discussion of the force method, because we are stick to this Schrodinger equation. So Feynman gives a simple approach to consider the force method to be more general as compared to the energy, and it has already been shown to you that using the energy approach we can find the energy eigenstate by the application of the perturbation theory, and the ground state by application of the variational method, as well as inside the molecule you will going to see that the Hamiltonian is very critical and the solution is very difficult. So we used to go for the Born-Oppenheimer approximation, Born-Oppenheimer approximation in molecule. Because for the molecules, what is there? Consider multi-atom molecule. So the Hamiltonian can be represented as V alpha alpha. So this is going to be the Hamiltonian, where alpha is taken as a nuclear coordinate and E is taken as a electronic coordinate. So it is corresponding to the electrons of the constituting the molecules. So it is corresponding to the electrons constituting the molecules. The first term corresponds to the nucleus, nuclei, that the nuclei constituting the atoms, because it may contains two atoms. So two atoms contain two different nuclei. So nuclei contribution is there, and this is the nucleus electron contribution of the potential energy. This is electron repulsion potential energy, and this is the nucleus repulsion potential energy. So all these things comes into the picture of the Hamiltonian, and it will be difficult to solve the exact Schrodinger equation. So we used to go with the Born-Oppenheimer approximation, where it is assumed to first consider the wave function to be first consider the wave function when electronic motion is alone is considered and the nuclei are kept at rest or just appear as a parameter only. And the second approximation was done keeping taking the wave equation of the nucleus and the electronic contribution, the solution of the electronic contribution that is obtained from the first approximation will add to the second one, and then we are going to the solve the Hamiltonian corresponding to the nucleus, in which some term will be added which comes from the electronic contribution. It will just add to the second one. So the solution will somehow be simple, but rather now also it will be difficult to us to solve this thing. So Feynman go with the force method. So in the steady state, as we already known to the these things, that for conservative force field the force can be written as minus of del u del lambda, where lambda is some parameter of the position.